Hello, everyone. Welcome to a new episode of our technology lunch. Today again in English with Lars Hupel, senior consultant at INNOQ. Lars will today look at some of the more advanced parts of TypeScript, of TypeScript's type system, and explain them based on a very common problem of data validation and processing. Before we start, please remember to post your questions in the YouTube chat. Lars and we will discuss the questions after his talk. And without further ado, welcome, Lars.
Yes, thank you very much for that introduction. And indeed, I will be talking about some advanced parts of the type system in TypeScript. And before I get started on the actual topic of my talk, I would like to give a brief review of what TypeScript is and what the design goals behind TypeScript are. I'm sure most of you have seen that website already. And what I like about the website of TypeScript is that it has a very concise description of its vision and mission, if you want. It just says TypeScript is JavaScript with syntax for types. So if you would ask that question, what is the vision of some other programming languages? I think many language communities would be hard-pressed to give such a concise answer, and this is what I really like about the system. Now, of course, there's a bit more behind that brief statement, so let's look into that. Of course, there can be some discussion, but this is my personal opinion here on what the core tenets of TypeScript is, and I'm sure they've also changed over time, but if we're looking at this today, this is what I would say, what I would identify as the core parts. So it is definitely JavaScript plus X, which means that if you take existing JavaScript code, it should run one-to-one unmodified in TypeScript as well. And vice versa, if you take TypeScript and then just remove the type annotations, you should end up at valid JavaScript code. Now, as a brief footnote here, not all the features of TypeScript support that. So there are some things that will have to be changed slightly when compiling down to JavaScript, but they try to keep that at a bare minimum. Second point is that we have a strong environment independence. So no matter whether you want to run your code on the browser, if you want to run it on Node, if you want to run it on one of the countless other JavaScript platforms, GraalVM, Ducktape, whatever have you, it should work in the same way. So they try to not pollute their type system with something, some like environment factors. Third point is the structural typing, aka duck typing. This is what the picture on the slide is. I shamelessly stole that from someone on Twitter. This is quite distinct from other programming languages. So if you talk about Java or C# or C++ in an academic setting, you would call that nominal typing. Nominal typing means that if you have a class, then the name of the class is somehow important. So if you have two classes with the same bodies, the same implementation, but with different names, there will be two separate classes. In TypeScript, that's different. If you have two classes with the same name, two classes with different names, but same body, same method, same properties, then they will also be treated the same. And I have some examples on that, and this will also be very important for the remainder of this talk. The fourth point is, of course, type inference. And type inference has many, many different meanings. In the most trivial meaning, I would say, sense of the word, I would say it is the ability to leave out types at particular positions. So for example, you can define a variable without declaring its type, and then the type gets inferred from the assignment that you do to the variable. So this is very basic, very trivial. Many programming languages can do it. There's more sophisticated notions of type inference where some programming languages, especially in the functional variety like Haskell or ML, you can just get rid of all types if you want, and the system will be able to infer everything from the whole program. even though you shouldn't do that, but it is capable of doing that. TypeScript cannot do that, but it is somewhere in the middle of those two extremes. And finally, which is also very important for the broader ecosystem integration, is that TypeScript actually supports all wonky JavaScript patterns. And I have some examples for that. Now, why did Microsoft, the original inventors of TypeScript, do that and like kind of get in return a very complicated type system? Is because they had to. So if history tells us something, then if we want to get a new programming language out the door and also get people to use it, then what you definitely need is an ecosystem. And what's easier than repurposing an existing ecosystem, right? Building a new ecosystem is very hard. So if you can leverage an existing ecosystem with the gazillions of JavaScript packages out there already, they had to do that. They had to look at what JavaScript does, what people do with JavaScript, and then support it in there. Now, having said all that, let's briefly try to motivate these ideas that they took from JavaScript and generally more broadly look at what people are doing with JavaScript. And what's really important when talking about JavaScript is that it is untyped. So I want to make that clear. There is no such thing as a type checker. There is, even at runtime, very little supervision from the engine, so to speak. The engine lets you add arrays to objects. It lets you multiply objects with numbers. You can compare anything with everything else. And the default comparison operator equals doesn't even make any sense from a mathematical point of view. So it's basically the Wild West of programming language. It's as untyped as one gets. And TypeScript basically set out to fix this, and fixing it, they did. So if I want to put this into a meme, then on the left-hand side is what JavaScript devs asked for, and on the right-hand side is then what JavaScript devs got. So maybe they were asking for a little type system as a treat, but instead they got quite a complicated type system. And it's basically, as I already tried to explain, it is what they had to do. Of course, there are other people, and then they say that in the true spirit of programming for the browser or for Node, you should not be using types. So they're a sign of defeat. You lost control of your life, and then you just use types to program JavaScript. Now, the guy on the slide probably didn't say that exactly. I might have put some mouth into his word, but I think you get the idea. So what's really interesting to me is that TypeScript is a language and an ecosystem that kind of piggybacks on an existing ecosystem. And you have some people hailing it as the new overlord of types, and then other people saying, why would we use this ever? So it's quite polarized. I don't want to take a stance in this talk on whether you should be using TypeScript or not. I just want to show off some cool things that you could be doing. All right, moving on to the next chapter of this talk, looking at the DOM. The DOM is the core part of the browser. It's what makes websites look nice, basically, and it's also what powers many front-end frameworks. So if you look at React, if you look at Angular, if you look at all of these things, they have to integrate with the DOM. And I don't want to look at these frameworks specifically. I want to look at the basics of the DOM. And why I'm doing that in this talk, it will hopefully become obvious at a later point, but for now, just bear with me. The DOM is actually quite a nice example of a very specific JavaScript programming pattern that is supported now in TypeScript's type system. Okay, so on this slide, I have a very specific example from the DOM. So one of the things that you can do in the DOM is if you have an element, an item in the DOM, for example, a button or whatever else you have, you can add an event listener to that element of the DOM. For example, you can call the add event listener method with two parameters. So the first parameter is the type of the event that you want to listen for, and the second one is the callback that gets invoked by the browser once an event happens. There's two other versions of this method as well. So there's a possibility to pass a third parameter, which is, if I remember correctly, an object where you can give multiple different keys. And then the third version is where you specify a Boolean, right? So the precise meaning of those parameters doesn't actually matter. But what's interesting is here that you have some form of overloading that is going on. Now, most programming languages or most type programming languages support some form of overloading, but in untyped programming languages, it's always a bit hard to write different implementations, and then you get dispatched to the correct one because the engine does not know the type of the thing. So what you typically have to do is you have to define one implementation of your overload method, and then inside that implementation, you need to do the dispatch. You need to check how many parameters have you received, what is the type of the parameter, and so on. Now, TypeScript also had that problem, like how do they fit that into the whole system? And here's an example of what an invocation of that would look like. So you can, for example, add an event listener that's called click, and you give that as a string. And then in the body of the callback, you receive the event, and you can, for example, access the event.detail a property of that event object. And in this specific case, the detail would be the amount of times it has been clicked. So it would be a number that you use. So that's kind of interesting. And if we zoom into this a bit further, you'll see that the event has belongs to the class mouse event, which inherits from UI event, which inherits from event. So you have quite a lot of things that are going on here, where first of all you have a string as the first parameter, and then depending on that concrete string, you get a different type as a parameter of your callback, and then in that callback you also have access to whatever properties that parameter has. Now, there's quite a bunch of these different event types. I've printed here an excerpt from the actual TypeScript repository where the types of this event handling are described. Now, quite a lot of code. Let me go through this one by one. In the top left of the slide, you see the different event strings. And what's interesting here is that we have an interface here, but the interface doesn't actually contain any data or values. So this is an interface that's only present at compile time. And what it does is it gives a mapping from the string, which is the parameter, the event type, and then it maps it to the actual data that you receive in the callback. So here you would see click maps to mouse event. If I instead have the event named animation cancel, I get an animation event. And what you see now on the bottom right of the slide is the actual definition of the add event listener type. And again, there's quite a lot of stuff going on here, but we have to do that because of the complexity that's behind that method in the DOM. So if we go through this one by one, we see that we have the type parameter, which takes a string basically, but not just any string. The string needs to come from this interface that I've just described. Then I get the listener parameter, and the listener parameter is not just any event, it's taking that event from that interface, and then we have the third parameter with the options. So if we zoom in on this a little bit, if I would be looking at that, for example, in VS Code, in many cases, you can actually hover over some things and then you see what it means actually. So it would unroll all of these definitions. So it's much easier to see. And here, if we zoom into that K type parameter, we would see, well, it's actually a union type. So you can specify abort, animation cancel, click. And if you would specify a string that is not part of that interface, you would just get a compile error. So it would just not work. So I find that quite interesting. And if we actually call that method with the click string, then that K, that type parameter K, gets instantiated with the literal click string. And then there's lookup happening, which goes into that interface and then kind of indexes it with the click. Now, what's really interesting, what's going on here is that global event handler's event map, so the interface, it's a type, and literal string click is also a type. So what we're seeing here is a computation on a type level. It's an index access at a type level. So there's nothing happening here at runtime whatsoever. There's no global event handles event map object that TypeScript somehow sneaks into your code and then kind of gives you additional runtime overhead or something like that. All of that's happening completely at compile time. And when I first learned about this, I was quite excited about it. Not because it's a totally new thing, like many programming languages can do it that already to some extent. So Scala or Haskell, for example. But what sets TypeScript apart is that all of these type computation facilities are really geared towards JavaScript, and they are trying to enable all of these JavaScript patterns. And if you think about it for a second, it is what you do in your brain when you're writing JavaScript code. And when you write an event listener, or when you register an event listener, you look up in maybe in MDN what are all the different event handlers, and then you copy paste that, maybe like any click. Okay, you can remember click, but animation cancel you might have to look up. You copy paste that literal string from the MDN documentation into your code, and then you check, oh well, I'm actually getting this animation event here, so let's look up what the parameters are. So this kind of flow from left to right that's going on here, that where you take out these strings and then check what events you're getting. This is exactly what the TypeScript compiler does as well. So in one way, it feels quite natural to be doing that. And it also catches a lot of mistakes if you have a misspelling, or if you're trying to use a feature that doesn't exist yet, or something like that. And another cool thing about this is that this is all library definitions. So there is a big file that's called dom.d.ts in the TypeScript source code. So d.ts means it's a declaration. So it's not actually an implementation function, it's just declaring stuff. And it's declaring stuff for existing JavaScript facilities. You could write that yourself, right? There's nothing special about that. The people at the people in the TypeScript community, they just sat down and checked all the documentation for the existing APIs, and then declared the types for them. So all of that fancy stuff that you see here, you could be doing yourself if you really want to. And in fact, this is what I'm going to do later in the talk. But this is not just for the browser. This is also for Node. So if you're writing some a code that's targeting the server side, and you do event listeners, you do streaming or whatnot, Node follows some of these same patterns where you have functions that take multiple parameters, and then the second parameter kind of depends on the first parameter. All of that exists there as well. If you want to have a good time, go look at the type definition for React, because React does that to an excruciating amount, to an excruciating extent. And there's so much stuff going on there to make that kind of work and type check. But on the other hand, you don't have to look if you don't want to. So you can also just import the type definition for React in your VS Code, in your package JSON, then VS Code will pick it up, and you get all of the type checking and all the like fancy squiggly lines for free, and you don't actually need to understand what's going on in the background. Now, assuming that you're still with me and you do want to figure out what's going in the background, I have compiled a pedagogical example for this. So here's some type definitions I will walk you through based on a real-world problem, which is data science. And the chapter kind of already gives it away, so I'm not sure how many people here that are listening have used Python for data science before. So in Python, there's a cool library that's called pandas, and pandas provides an abstraction that's called Dataframes. And Dataframes are basically fancy tables. To make long story short, Dataframes are fancy tables, and pandas provides a huge amount of library support for working with these data frames. And I just thought maybe we can implement it in TypeScript as well, but with types, of course. So the key insight here is that if you want to do data science TM, so I'm all for them things a bit tongue-in-cheek, so I'm not a data scientist. I have no idea what I'm talking about. So data science is basically just tables, right? Shoving data around in tables. And CSV is obviously a great format for tables, but what are we actually going to do with this data in CSV format, so the fancy tables? So I just put together a list of some operations that are quite typical. The first one is, of course, very simple. You want to access a particular data point. So you select row I, and you go to column C, and there's like one scalar value in the table, and you want to access that. Or you might want to filter your rows by a predicate. So you want to say, I want to keep all the addresses that are in Germany, and you want to filter out all the addresses that are not in Germany. Or you want to drop columns. For example, you have done a big import from a SQL table, and there's just a bunch of random junk in there that you're not interested in. You just want to remove it. Or you want to add a new column. For example, you want to compute the length of the name of someone. Right? You have a name column, and then you want to compute the length of it and add it as a new column. Or you want to aggregate or group by a column. So you have maybe a denormalized table, and then you want to do some SQL style aggregation on it. So all of these are perfectly typical operations. But now you want to look what they do with the types, because in pandas, there's no type checking of that sort. If you make a mistake, you just get an exception at runtime, which is, I guess, fair enough if you're doing some experiments in Jupyter. But if you want to have something that works in batch mode and can cope with that sort of issues, then types could be of help there. Now, if you try to abstract over all of these different operations, you could think that there are functions that take a table and produce another table. So very simply. If you look at the first operation, namely taking the row I and taking the column C, then it would be a 1-by-1 table, so just a very small singular element in a table. But the other ones could produce more complex tables as a result. If we zoom into this a bit, I mean, we're here in a talk on types, so of course I want to show you what the typing of that would look like. We could first start to add more information to the table class, or to the table interface. And I'm going to give the table a type parameter, which I put in those brackets. And I'm not going to tell you right now how this is implemented, but just bear with me for a moment. The operation takes in a table with some columns and returns tables with some other set of columns. So this type parameter that I've given here is supposed to represent the columns that I can access. So we're here dealing with kind of a column-based approach, where I can always check if a particular table has a particular set of columns. Now you might wonder, why is it the columns here, not the rows? Very simply because all the rows have the same shape. So every row has like 5 fields with particular types. So this is all the same, but the columns are different. So I have a name column that is a string. I have a zip code column that's a number, or maybe a string also. And then I have an age column that's definitely a number. All of those things, they are different. So this is why it's fairly intuitive to put the column types there in the type. Right. But I'm not done yet. I want to also show you what this type parameter actually represents. So if we actually if you were to write that down in TypeScript, we would define an interface called table, and then I specify the type parameter, and I say that the type parameter must extend a record type. So record is a built-in type in TypeScript, and the record should have strings mapping to any type. And record string any is basically the type of an arbitrary object, because objects map string to any. Well, footnote, objects could also contain symbols and stuff, but let's not get ahead of ourselves here. Basically, what I'm saying here, the column's type parameter must be the type of a particular object. And in that particular object, I can say I have these 5 properties, and they have these 5 corresponding types. And don't worry, I'm going to show an example now. If we have a table here for orders, then we might have a column with the index. We might have a column with the string order ID, could be UUID or something like that. We have an item and a quantity and a price. And you already can see that our table here is denormalized. So we have 2 separate rows for particular order ID, but it doesn't matter for now. Let's just take that for granted. And if I were to write that down as a type in TypeScript, I would say this is a table. And here's the object type now that represents all of the columns. So we have 4 different columns here. I've moved out the index column for now. And I say that there's an order ID, which is of type string, and item of type string, quantity and price of type number. Now, I put the index column out of this because the index column is special. This also applies to pandas in Python because, for example, you cannot do any grouping on the index table. So it's like in SQL where you have like a primary key index or something like that. So in a real implementation, you would have to treat that specially somehow. All right, so now I've only shown you the interface. And given that I come from a functional type programming background, we've always had this saying that if it compiles, ship it. So you won't even need to run it. You just need to make sure that the types line up. So I could just be writing that interface table and then not worry so much about the details of the implementation. I just need to make the types line up, and that's good, and it's gonna work. But of course, I want to also show you some more details of how that kind of stuff can be implemented. So let's take a look at that. The basic building block in order to or make that work is a type or an interface for a single column. And that single column is called a series, and I've also stole that naming from pandas. So this is very simple because the element type is just some scalar value. So it can be a string, or it can be a number, or it can be, I don't know, some unstructured object or something like that. So I think this interface does not look too complicated. Now, it has two separate operations. First of all, we can create a length of that interface, and I've declared it as a get method, as a getter, so that it looks a bit more similar to an array. You might ask, why is it not an array? Well, this is for pedagogical purposes. I wanted to show a specific implementation of this. In a real implementation, you might just want to use arrays, or if you want to do something fancy with sparse data, matrices, whatever, then you might have to do a concrete implementation. I'm fairly sure that pandas is doing some fancy stuff and using, they probably have good reasons to have a separate type instead of just using an array. Yeah, and then also you have a method that can access a particular element at a particular number. And I've already simplified this a bit because in reality, you would need to think about what is happening when you're accessing an element that's out of bounds. Now, if you were using the normal semantics of arrays in JavaScript, the answer would be just throw an exception, it's fine, or maybe just return undefined, it's fine. So depending on what you want to do. If we were to throw an exception, we could do that in this type signature. If we want to return undefined, we would have to specify that concretely, because undefined, at least if you switch on all the safety checks from TypeScript, then it would not allow you to return undefined if undefined is not declared as a return type. So in that case, you would have to do a union of elem and undefined. Okay, so this is the series type now. And let's move on to the table type or the table interface. And here you can see what I've done with the index. So I've given the table two type parameters. The first type parameter is the type of the index. And then the second type parameter you've already seen is the columns that extend some particular object type. And let's also look at the various definitions here in this interface. We again have a getter for the index series, and it doesn't have to be a number. It can be anything, just it has to be distinct and so on. And now I have put two possible operations here on this interface. So the first operation is the select operation, where we just take a look at a particular column. And this already shows you some interesting bits in TypeScript, and it kind of circles back to what I showed you initially, where we were looking at the DOM. Now, what does it say here? We have the select operation here, and select takes a type parameter, which is called col or column, and it then takes that as an argument. So that might be strange. So it's a type parameter, and then you just also take it as a normal parameter. That seems a bit weird, but I will show you in an example, in a demo, why this is actually the way, why this works. And this call cannot be any old value. It needs to be a string that comes from this calls type. So here in the table, we have the columns which extends record string any. So we have a bunch of columns defined in that type here. And then when I want to select, I need to specify one of those. So I cannot specify a column that doesn't exist. If we go back to this example, if we have this table, the only strings that we can specify are order ID, item, quantity, and price. So these are the 4 options that you could be specifying here. If you would specify a column that doesn't exist, you get a type error. And then it returns this method then returns a series, so basically our array-ish type. And the series also has a type parameter, and we're taking the type of that column. So calls is an object type, and we're selecting the type of that property that we just requested. Okay? And the second operation, the lookup operation for looking at a particular row, it's a bit simpler. So we just take a row index with that index parameter, and we return we return a particular row. Now, row is also a dedicated interface that I provided, that I implemented. You could also just return the raw object type if you wanted to, but yeah, just for pedagogical purposes, I also split it out. Okay, so you still haven't seen the implementation, actually. So if you give me a moment, I will switch over to my code now, and then you should be able to see it a bit more clearly. So yep, that's the code view now. And I can actually show you that I didn't cheat. So the implementation that we're going to look at is exactly what I showed you in the slides. So there's a bunch of code here. You see the series, you see a particular row type, and so on. You also see the table type. But I actually don't want to spend too much time on the implementation, so I'm going to close this again. I first want to show you how it can actually be used. So now we go into TS Node, which is just the TypeScript shell that runs against Node. And I have to do a particular import. So I'm just importing these definitions from the index file. And now I want to import something, and there's also something I prepared. So let me just paste it here. I'm importing a table, which is basically an array of objects. And you could imagine that this could also work for actually reading data from the file system. So I've just put it here so that you can see this is exactly the same example from the slides. We have 3 entries in our table, and there's these 4 different types. Now you see already here that type inference has happened, right? So I didn't have to specify actually the type of table 1. It's something that can be inferred. Now, if you would be running that, for example, in VS Code, you could hover over table 1 and see the type of that. There's one operation that I've implemented that's just called dump. So we can also dump the table and see that this is exactly the same thing that's in here. This is what you see here on the right-hand side, the symbol. This is the index column, which I defined specially, but I already mentioned that. Now we can see that we can select something. We can say if table1.select, and then I get a series with just the quantity. Now, if I were to misspell that, I would immediately get a type error. And now you can see the magic of the type inference that's happening here. So we see that argument of type Qt is not assignable to parameter of type blah, 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 blah. So 2 things have happened here. The first thing that happened is that we have the type inference from this construction, where TypeScript automatically deduced that we have those 4 different column types going on, or those 4 different columns with names and types going on. This is the first part, and this is what we get here as this union type, where we have order, item, quantity, and price. And the second thing is that type inference also is going on here when I actually call select, and it says, well, Qt is a string. It's not just any old string, it's the literal string Qt. And if I try to shoehorn that Qt into that type I've inferred earlier, then it doesn't work. So I get the exception here. right? Of course, again, if you're running this in an IDE, it would be quite fancy, and you would get like code completion and something like that. So that would be supported. So if I were to write table1.select now in code or in IntelliJ or whatever, then I could just press Control space or Command space, and I would get QTY automatically completed. So not only gives that compile time safety, but we also get development time convenience from the same kind of concepts. I can also now just assign the table to a particular variable. I'm giving that a name, and I could also just specify the type if I wanted to. So let's try that. Let's say this is a series of what is quantity? It's a number, so that would work. But if I would try to assign it to a type that's actually not the same thing, then again I would receive an error message. So I would see that this is not assignable to type 0 string. So all of that is kind of working in the background. There are some special cases, I must admit. So sometimes you have situations where you actually cannot specify that string concretely. You would have to read that from a variable. That sometimes happens if I take user input, for example. If I take user input, give me that particular column, then I would have to do some pre-processing and check if that's actually there, if that column already exists. I would need to write some additional code. But that's just the price of validation, right? I mean, even in plain JavaScript, you would have to do that sort of validation that the user input you take is actually present and not just throw an exception if the column doesn't exist. Okay, so far so good. So I've shown you the select function, which is not overly exciting because we can't do much with it. But we can actually, I can actually show you another operation that I've implemented, which I haven't shown you yet on the slides. And that method is called insert compute. And what it does will hopefully become obvious while I type it in. So I say insert compute. I want to insert a new column, and the column should be populated from existing data that I have in my table. So it's not just, I don't want to specify the data manually myself. I want to give a function that computes that. So I want to say that I want to insert total price of the line item of that order. And now I give a callback. So now I can actually get the object that corresponds to the shape of the columns I have. So I can destructure this object immediately here. So I say I get an object that has at least quantity and price. It might also have other things, but I don't care at this point. And then I return quantity times price. And if I haven't mistyped, then yes, it actually worked. Now I have a new table. And actually, I should assign that to the variable so that we can manipulate it. I call it table2. And I can also dump it. So I say console.here table2.dump. And then I would see I get some additional columns here. So I have the apple, which is now 5 times 10 equals 50. And then I have the pear, 2 times 3 equals 6. And I have another apple, which is 1 times 8 equals 8. So that has been computed successfully. And again, I can now select that. So while in the table 1, I cannot select total price because it doesn't exist. If I go to table 2 and select total price, it exists. So I can access that data now. That's already some non-trivial transformation that we're doing here. We can also do the opposite thing. We can also drop stuff from the table. So I can say drop price, and I can drop order, for example, if I want to. Let's also do that just for sake of curiosity. So I drop that, and type inference here again works automatically. So we can see console.dir table3.dump. And now I have just the quantity and the total price left. Now, I've also implemented an operation how you can do a group by. Now, the group by is a bit more complicated to understand because in the group by case, I'm not sure if you still remember SQL. Writing SQL code manually, it seems to me that no one is writing SQL manually anymore these days. But in an SQL query, if you have a group by with particular columns, then you need to make sure that that you're aggregating correctly. So SQL has some particular ideas of the columns that you're using in a group by, and the other ones they must be aggregated then. So you need to, for example, specify the sum function in order to do that. And in this example, we could, for example, calculate the total quantity, the total price of a particular order. Again, this is a denormalized table. And then we would need to say that everything that's not grouped needs to be aggregated somehow. And I've actually implemented an operation, and I will just try to copy paste it again here without spending too much time on this. Basically, the type system of TypeScript can check for you that you're doing that whole aggregation correctly. So seems I did something wrong here. Oops. This is the cost of doing live demos, I suppose. So let me just restart that. Paste in stuff again. At least I have some prepared code that I can just paste in. And now we go type this again. See, hopefully it works now. Nope, it does not work. Okay, I'm sorry about that. So I just have to show you the actual code instead of showing you it running. Go to test.ts. So the code that you're seeing here is what I just typed. So you see at least that I'm not completely cheating. Now the way that this works for the group by operation, we say that we can group by a particular item. So item is then here the string, the column, and then as an object I specify the aggregation function. So I say I have to aggregate by quantity and I have to aggregate by total price. So the quantity I would just add up, and the total price I would also add up. And I don't have to specify the aggregating function for the other columns because I've already dropped out those columns from the table. So I've dropped the price and the order ID, so I don't have to aggregate by that. All right, and with that, I'm done with the demo, and I'm also done with the talk. So thank you for listening. I apologize for that last example not working, but that's the price of doing live demos, and happy to answer any questions now that you might have in the chat. Unfortunately, I cannot hear. I cannot hear you, I think. Now I can hear you.
Usual problem. So thank you very much, Lars. There were no questions in the chat, but I do have a question, and maybe while you are answering, if all the other people have questions, please write them in the chat. So if I have existing codes, how can I go, let's say, step by step from JavaScript to TypeScript?
Yeah, that's an excellent question, and I get asked that a lot because obviously doing a big bang migration from JavaScript to TypeScript on everything is not going to fly. So there are a few different strategies here. The one I like most is if you start with your domain model. So if you have a model of your business domain, for example, you have these orders or you have customers or something like that, then you could start out by just declaring the type for those. So you wouldn't actually have to rewrite your JavaScript code to TypeScript and have it run through the TypeScript compiler. You could initially write these d.ts files, so these declaration files. They can work alongside existing JavaScript code. Of course, the downside here is that you don't have compiler checking, that what you're declaring is actually what you have implemented on the JavaScript side, but you can merge it at a later point. You start out with these declaration files, and then you can use them, for example, in your tests. That's one possibility. If you want to be more ambitious, you can also just rewrite your domain model in TypeScript. This is typically not so difficult because what you're doing there is you have classes with maybe a bit of business logic, so that should not be too difficult to translate to TypeScript. Another strategy that also works is if you start with your front end. So if you have, for example, a React-based front end, you can switch on the flag in the TypeScript compiler that makes it accept existing untyped JavaScript code. It might try to infer something from your JavaScript code, but also otherwise it will just see any. So it's just the dreaded any type. And then you can, for example, pull in the type definition for React. And then at least the interaction with React is well typed. Then maybe the interaction with the rest of your code is not well typed yet. And there are many other such strategies. For example, some people like to start with their tests, so that their test framework is well typed and so on. But basically, the teams can decide for themselves how they want to do it. And I think this is quite a nice property of TypeScript because Microsoft and the open source community at large have taken great care of implementing the tooling in such a way that you can have a code base that is mixed JavaScript and TypeScript. If you have, for example, a code base that is implemented in CoffeeScript or something like that, I don't know. I have no experience with that. But if you have just JavaScript and TypeScript, you should have no issues because all the tooling these days understands TypeScript.
Okay. Yeah, it reminds me a little bit when I want to move from Java to Kotlin. So there the ideas are overlapping, let's say. Okay. So Harshit asks, would you be able to point some documents for advanced TypeScript, like from where we can, where he can start the TypeScript game?
Yeah, good question. Actually, I like the TypeScript documentation on their homepage quite a lot because they have, I mean, they say it's a reference manual, which is true. They have like they go through all of those type system features, but they also give you examples of when you would want to use that. So the way I learned this is I went through the handbook and the reference manual and just checked what's out there, and then just get this in the back of my mind. Okay, so there's a type that's called omit. There's a type that's called pick, and all of these things. Or you can do this array notation on types, and ultimately then once you have it in the back of your mind, you just need to practice it. So this is what I found works best. I've written an article on this that you can also find on the INNOQ website on this topic. But generally speaking, most of these blog post style introductions I found are they work with artificial examples, like I've also done here in this talk. So the best way to actually get started is to find an itch to scratch in your code base, and then after having read the handbook, you see there could be something that works here, and then you just try to apply an iterative refinement, because you can write boring TypeScript. You can write TypeScript in a way that you don't use all of that fancy type, and it still gives you something. And then maybe you already have an existing code base like that, and you just pick something and make it more advanced. Maybe that's the strategy I would recommend.
All right. Thank you. So no further questions. We are also a little bit over time. So I want to thank Lars and the audience. If you haven't done so far, please subscribe to our YouTube channel and to our meetup. If you're keen on more of Lars and also others, please visit our technology day in about 6 weeks, 7 weeks. So it's November 30th. I'm pasting the link as well. So there is more Lars and more of others. We have 7 parallel tracks, 6 in German, 1 in English. So happy to see all of you there. And for those who are in Hamburg or around Hamburg next week, there will be a meetup on site in real persons meet in the evening. So with Michael Plöth and Jochen Christ, mainly around domain-driven design, data mesh. So if you're in Hamburg, please, if you're in Hamburg next week, please go there. All right. So then I would say thanks to everyone and have a nice rest of the afternoon.
Thanks.